Yeah, so first talk of the session is by Subhro Bhattacharjee. So he's going to talk about classical many-body chaos with and without quasi-particles.
Okay, thanks, Sanjeev. And let me start by thanking the organizers for inviting me to this meeting. Unfortunately, I've not been around too much because of some ill health. Let me try to tell you about the story which sort of fits with the theme of this meeting that we have been doing for over the last few years, that's trying to understand and characterize aspects of many-body chaos in strongly correlated spin systems, classical spin systems of two varieties. One which shows good long-lived normal modes or quasi-particles, and the other where we don't know if such quasi-particles exist, to be more precise, in the sense that we haven't found any so far, and this is why this word is in quotes. Okay. So there are lots of people involved, almost everyone from the stat mechanism matter corner in ICTS, and I've highlighted the students and postdocs involved, and these are some of the older things that we have published so far, and I'll briefly talk about an upcoming preprint that we are going to put up shortly. Okay. Almost exclusively, I'll be talking about classical spin systems, which are three-component vectors living on some lattice, 1D, 2D, or 3D, and the spins on different sites interact with some short-range Hamiltonian, which are spin rotation symmetric, and the classical precision dynamics is generated by this Poisson bracket, and we will try to understand what their dynamics is and how to try and understand their the chaotic behavior in these systems. But let's start with some of the basic summary. So we take these systems, and at very high temperatures, all of them are thermal paramagnets in the sense that the spin expectation value is 0, and the spin-spin correlations are short-ranged. But when we take these kind of systems and try to cool them down, typically they behave in one of the two kinds that I have shown here on the left, which are basically more well-behaved set of magnets called the unfrustrated magnets, where all these interactions are sort of compatible and they are not competing with each other. So in those class of systems like square lattice Heisenberg magnet, etc., or cubic lattice Heisenberg magnet, what happens is that as you decrease temperature, at certain temperature, the system orders into some antiferromagnetic or ferromagnetic configuration, and you characterized by a non-zero expectation value, thermal expectation value of the spins. And this in experiments is signaled by this kind of behavior in the spin susceptibility at around the temperature, which is of the same scale as the exchange constants. So those are the class of systems that we know a lot about. But another interesting family of such magnets are these frustrated ones, where these interactions are incompatible in the sense that different interactions, different sets of interactions are not compatible with each other, and hence they compete. So in such class of systems, when you cool them well past their characteristic energy scale, which is the exchange scale, they continue to remain in this paramagnetic phase because they cannot, because these competing interactions cannot decide which order to go into, and at a much lower temperature, the subleading interactions which might be present here dictate select some order due to thermal order by disorder or such mechanisms, etc. Okay, so this opens up this region, intermediate temperature scale, which is less than the exchange scale, but bigger than the ultimate ordering scale, where the system is paramagnetic, but it is correlated in the sense that the spins are really interacting with each other and interacting with each other but not ordering. Okay. So what one can do is by suitably fine-tuning this interaction, make this correlated paramagnetic regime go all the way to 0 temperature, and in that case, we basically get a macroscopically degenerate ground state manifold and a finite 0 temperature entropy density in the thermodynamic limit with non-trivial spin correlations or some other correlations that are present. And this is what I'll keep on calling a correlated paramagnet or a classical spin liquid alternatively. Okay. So, so as far as the low energy excitations are concerned, in the unfrustrated magnets, what happens is that once I have this global order, I basically have these spin waves which are coherent normal modes, and they are the lowest energy excitations. On the other hand, if I think about the frustrated magnets, there is a huge set of ground states, and the system keeps on fluctuating in the vicinity of the ground state manifold, and the width of this fluctuation is governed only by temperature. And it is in this regime, it is very hard to, so far has been impossible to identify well-defined quasi-particles in the sense of spin waves. And this is why I would keep on referring to them as no quasi-particles. Okay. So the question that I would start with is, what is the effect of this discrepancy of behavior between the two families on the many-body chaos? In particular, when there is symmetry breaking, the entropy density goes to 0, and there are ballistic quasi-particles, whereas on the other hand, both these things are absent at low temperatures. Okay. So again, there are many ways to try and understand these spatiotemporal chaos in many-body systems. By the way, since the Hamiltonians are local, the chaotic behavior is going to have both temporal aspect as well as a spatial aspect. And the way that I would try to characterize is by trying to understand how two configurations which are different locally, only at one point in the system, start to deviate from each other. And this deviation would have a temporal aspect, as I said, where the deviation that I started out, say, at the origin, grows at origin, but also it spreads to other parts of the system. Okay. So, one way to characterize this quantitatively was trying to think about this two-copy correlator, which we keep on calling the decorrelator or the cross-correlator, is that you take a spin system, generate a configuration, say infinite temperature configuration like this, and then make a copy of the same configuration and deviate and rotate one spin, the one, say, at origin, by a small amount, and then take these two copies and run the same precessional dynamics for the same Hamiltonian for the same time, and at the end of it, calculate the dot product of the respective spins from the two copies and average it over the ensemble. Okay? Or you can take the difference, and this is what I'll try to keep on telling you. This is the decorrelator that I'll keep on mentioning. Okay? So at infinite temperature for the Heisenberg magnet, the nearest neighbor ferromagnet, the usual two-point correlator is diffusive, and there is no sign of any ballistic behavior. But if you calculate this difference between the two copies, with the difference starting only at x equal to 0, and you run time, the difference keeps on spreading ballistically. And if you average over configuration, you see this well-developed light cone where the difference is exponentially large within this light cone and exponentially small within this outside it. And the form of the decorrelator, the configuration average decorrelator is given by this quantity, characterized by the temporal growth, the Lyapunov exponent, and the butterfly velocity, which characterizes a spread. This is for the infinite temperature Heisenberg ferromagnet, nearest neighbor. Okay. So let me go back to this picture again, and then now try to tell you what happens to these two classes of magnets, given we already discussed the infinite temperature results. I'll now decrease the temperature and discuss these two cases separately, starting with the correlated paramagnet. Okay, so this is the summary. So what happens is that, as you would see, that in this correlated paramagnet, this remains chaotic from very short times, and the Lyapunov exponent and the butterfly speed both disappears as the temperature goes to 0, but slowly, and there is no simple kinetic theory description that emerges yet. There are diffusions of spins and energy, which is then determined by directly by the Lyapunov exponent and the butterfly speed. On the other hand, when the magnet orders, and this is what I'll mostly concentrate on in the rest of the talk, is that at short times we see a sort of an integrable behavior coming from free spin waves, and that gives away to a scarred regime where the spin waves starts scattering from each other, leading to a long time chaotic behavior where you see full exponential growth. And this has a kinetic theory description which can be captured within some mode coupling approaches. Okay? Okay, so I'll try to flesh out these things. Okay, so just to tell you briefly about this correlated paramagnet, what happens, the reason for this behavior is basically the fact that there are a large number of ground states, and so there is a huge entropy even at very low temperature, and the system remains more disordered or chaotic, and even though non-trivial correlations develop in the system, and this shows up in this measure of chaos. Okay, so the particular model that I'll take, which shows this correlated paramagnetic behavior all the way to 0 temperature, is this frustrated Kagome magnet, which is on this corner sharing triangular lattice. And what we know from earlier results is that this has a macroscopically degenerate ground state manifold, and the spin-spin correlations are finite. The correlation length is finite even to the lowest temperatures, and these are the spin-spin correlations in momentum space. Okay. So if I calculate the dynamics and calculate the 2-point correlator, it shows spin diffusion, but the spin diffusion, the diffusion constant is temperature independent. And one way to understand that, and this is the numerical data, is that even at low temperatures, the system sort of meanders about in this ground state manifold with little or no energy required, and this is the reason why the diffusion constant is independent of temperature, and this is what the numerical data also shows. Okay, so on the other hand, if you actually calculate the decorrelator, what you find to a very good approximation is that the Lyapunov exponent is goes as square root of temperature, and the butterfly speed goes as 1/4 of temperature, and this is the spread of the decorrelator front averaged over various configurations. Note that the underlying Hamiltonian has only C6 rotation symmetry, whereas even if you look at a single configuration, it's quite symmetric, particularly at long times. Okay. Okay, so so similar questions arise in a bunch of other contexts, and where the system remains disordered to very low temperatures or doesn't show any kind of ordering or quasi-particles. And in fact, this square root temperature is also seen in these thermalized Euler equations that Samriddhi and I looked at with students, and even in this very different context, this square root temperature behavior shows up in the Lyapunov exponent, but there is no butterfly velocity because the interactions are non-local. Okay. So, that's the brief summary of what happens for a correlated paramagnet. But let me now switch over to this other side, which I want to tell you a bit more about. What happens is that literally if you calculate the decorrelator at short times, it really looks like this. Okay, you don't see any feature of any exponential growth. Instead, you see these wave-like patterns, which are basically spread of free spin waves. And as you run the simulations for a longer time, that gets replaced by this intermediate scarred regime, where you see lots of these secondary light cones within the primary light cone. And finally, it gives rise to this diffusive core, where the most of the weight of this exponentially growing decorrelator is concentrated on. And there is, of course, a pilot wave, which goes with a ballistic speed. Okay. Okay. So the starting point to understand these systems, because they are below the ordering temperature, is to think about deviations from the zero temperature ordered state. And so this is one. In this way, you write the spin as the ordered moment and its deviation, which is the spin wave amplitude, which is perpendicular to the ordered direction. And then you try to understand the deviation of the equation of motion for this decorrelator, the difference of the two copies in such a background. And this leads to these kind of mode coupling equations, where essentially this is the Fourier component of the decorrelator, or if you take square of this, that's the decorrelator, and it has a free component part, which is basically the difference of the two copies evolving in a frozen background of ordered state. And then there are interactions, which is deviations from the ideal zero temperature configuration. And this leads to the scattering between the decorrelator wave that is spreading throughout the system, and this kernel is the nonlinear spin wave kernel, that it is actually the same kernel that shows up in, if you try to calculate the spin wave lifetime in a nonlinear spin wave theory. Okay. So then if you take the square of this and take the Fourier transform back, there is a linear part of the decorrelator, which is non-exponential. And then there is this correction, which ultimately takes over. And the question is that, is this the right way to think about how the long-time chaotic behavior is obtained, and the intermediate regime? Okay. So at ultra short times, this is exactly the free propagation for the ferromagnet, which is free Bessel waves in square lattice. And you see, this is the free theory, and the full simulation for the short times. And the agreement is sort of suggestive. You can make this more quantitative by comparing cuts, which you can find in this paper. And this is for the antiferromagnet, where because of the difference in the form of the spin wave velocities, the front shapes are different from the ferromagnet. And again, you see quite a different behavior compared. You see quite an agreement between the free theory and the full simulations at the short times. Okay. So then once you increase time, what happens is that at this temperature, you can already see that around about this time, the numerical data starts deviating from the free spin wave. And simultaneously, in each configuration, you start seeing the secondary light cone events within the primary light cone. And roughly this starts, I'll come back to this at a characteristic time scale. And then the question is that can we understand the origin of the secondary light cones more carefully from the scattering events coming from these imperfections due to thermally excited spin waves. Okay, so one way that we recently found out that this can be understood a bit more carefully is that instead of taking a thermal configuration, let's think about a configuration where you have an ideal ferromagnet, say, except for one spin, which we call the defect at some point xd, which you rotate by a small amount and then try to calculate, try to run the simulation with this configuration. So this is the decorrelator, the difference of the two copies only at x equal to 0, and then this is the deviation of magnetization from the background, which is only present here. Okay, so if I now run the simulation, what happens is that this decorrelator wave is spreading out from 0. This is a Bessel wave, and this is the deviation of magnetization, which is spreading out from the defect. And this is and as you run time, they basically intersect with each other, each having its own light cone. And when you try to calculate the decorrelator, this is the time that they meet, and they cause these secondary waves for a single defect. When you have multiple defects, what happens is that they cause scattering, and then they scatter inside the light cone, and that leads to this very scarred region in both ferromagnet and antiferromagnetic Heisenberg chains. Okay, so essentially, this hints that it is indeed this this nonlinear evolution of this kernel which is responsible for causing these scarred regimes, and which eventually leads to this exponential growth. Okay. So finally, of course, at some point you, by the way, with this defect, instead of having a thermal the density of spin waves, you can control this. You can do a lot more calculations with this mode coupling equations and get a distribution of these secondary light cones, which I'll be happy to discuss after the talk, but eventually that breaks down at longer times because there are way too many, and you get the exponential behavior. What we realized is that the same since the same kernel shows up at the when calculating the spin wave lifetime, it is basically it indicates that the Lyapunov exponent seems to be the maximum of all the scattering rates at different for the different spin waves that seems to control the Lyapunov exponent. This is not a proof, but this is just an observation of the from the fact that identical kernels enter into both these set of equations. Okay. So as far as the Lyapunov exponent is concerned, it still is a positive power of temperature, but this power is greater than 0.5, and in that sense, it's less chaotic than the correlated paramagnet, and both in case of ferromagnet and antiferromagnet. And the butterfly speed saturates to some value, which is given by the spin wave for the antiferromagnet, and the order of the exchange constant for the ferromagnet at 0 temperature. Okay, so let me make end with two comments about the chaos in correlated paramagnets before my time runs over, is that the decorrelator that I have shown is basically the classical version of the out-of-time commutators, and you can go back and forth, replacing the commutations with the Poisson bracket in the quantum case, there are these bounds that we know that quantum systems obey, but the classical exponent, the exponent that I showed, this 0.5, indicates that at low enough temperature, it might violate this bound. And one possible resolution that these classical paramagnets seems to take once we think about semi-classical fluctuations or 1/s fluctuations is that they lead to quantum order by disorder, leading to interesting crossovers at low temperatures from mostly the classical regime for which this calculation is valid to the quantum regime, which usually is gapped. And we have one calculation upcoming, which I can tell you about. Okay. The other, I'll be done. This is my last slide. The other comment that I think is interesting is that in this correlated paramagnet, there are no well-defined quasiparticles in the sense that I mentioned, and there is no good description in terms of a kinetic theory of these weakly interacting quasiparticles. However, spin, the model doesn't break, the system doesn't break spin rotation symmetry, and there is still spin diffusion. And what seems to be a numerical observation that the spin diffusion constant is is controlled by this butterfly velocity squared divided by lambda, and which, the scaling wise, this makes sense for the correlated paramagnet that I showed. But if you actually calculate this numerically, the two quantities, the butterfly speed, lambda, and that's d minus in this case, and then the actual spin diffusion constant from the 2-point correlator, they seem to be agreeing quite well. And so it looks like that in absence of these quasiparticles, in the sense that I mentioned, the diffusion constants are directly governed by the chaos time scales and length scales. Okay, so with that, I'll try to put up my summary, and thank you for your attention.
Hi, two questions. So one is, so if you are able to track the time between scatterings, do you expect that to be also a random variable as you approach the chaos boundary?
Sorry.
So if you are able to measure the time between two scattering events in the scarred area, so is that expected to show any random?
Yes,
behavior?
so for ferromagnet, we have an exact expression because for ferromagnets, these are Bessel waves, and it's equivalent to calculating Bessel zeros. Okay, so we have a closed expression. So if these are randomly placed, we know an exact distribution of these times.
Okay, and second question is that you had this intuition of lambda as this made out of these 1/taus. So does it allow you to derive this t power half?
No, so that's where the spin wave approximation is valid, where we can do this mode coupling and identify the kernels with each other. We don't have such an expression when the spin waves are not there for correlated paramagnets.
It's the case where you're doing kinetic theory. So there you are saying the relation between D and the V square by lambda, that's not valid, is it?
So it's valid in the way that V is replaced by sort of the characteristic velocity, the spin wave velocity, and lambda is 1/tau. Yeah. So but V squared over lambda seems to be a more generic way of saying the same thing, which holds even when the single particle scattering time or the RMS type of velocity, as you would get from kinetic theory, is not.
So it's valid even when the kinetic theory, but in the kinetic theory, one can just understand it.
Absolutely, absolutely, because the lambda and the V are related to the kinetic theory. That's the mode coupling.
So thanks for the talk. So actually, I have a question on your last point of your summary. What about quantum system? Do you expect the same phenomenology of three regimes like this integrable, scarring, and chaotic for quantum antiferromagnets at low temperature?
In quantum antiferromagnet?
Yes, but I'm asking because not only you have spin wave, but also you have this rotor mode in a symmetry broken state.
Yeah.
So I was wondering if this could interplay differently then.
So if I do a large S approximation, take 1 over S, that intermediate regime doesn't seem to vanish to the leading order in 1 over S.
Does that include, the Anderson Tower of States modes or not really? Probably not. I think at low energy, you have this Anderson Tower of States for symmetry, which is not here. So I was wondering if this could interplay
in a thermodynamic limit.
No, but
okay.
It collapsed to the ground side, of course, but
sure. I think that the mode coupling equations are already at thermodynamic limit, and in that case, that seems to suggest that it does not go away, but it's just 1 over S correction.
Could you please, I just didn't understand the argument about the bound on chaos. The bound on chaos is a T over H bar, so you have a classical spin, so why do you say it's breaking the bound?
Oh, no, I'm not saying that it's breaking the bound per se. I'm saying that this is the classical limit, but if you want to take semi-classical corrections, okay, I think you have to restore the bound, okay? So the question is, how do you restore the bound?
Okay, yeah. Thanks.
Okay, so I have a just quick question. So do you have is there a physical understanding for the square root of t or t to the power 1/4 for this butterfly velocity?
Square root of t, there is understanding for simpler systems in trying to map them to negatively curved manifolds in phase space. But we don't know what these the manifolds of these correlated paramagnets look like. That's something that we have tried a lot. We haven't been able to show that they are negatively curved. They can be mapped effectively to dynamics of particle moving in a negatively curved manifold in phase space.
And same with the butterfly velocity.
Yeah.
Okay. So let's thank Subhro for